Position as a geometric tolerance controls location, and it is the only geometric tolerance which controls location. Now, before 2018, when the latest version of ASME Y14.5 came out, before 2018, there were 3 location controls: position, there were also concentricity and symmetry. Those controls are very, very bad. They had terrible problems, and there was a big political fight about them that went on for years. And finally, with the new edition of ASME Y14.5, they are gone. I just tell you that because you may run into them, and you need to know they are no good and they are no longer with us. So we are going to use position to control the concentricity or the symmetry or the location of anything. Position is the most common geometric tolerance. If you use any GDT control, you will use position. Now you remember what a feature of size is. It's a thing that you can measure with a caliper. Position only controls features of size, so you can't use it for just plain surfaces by themselves. And what it really locates is the axis of a round thing or the center plane of a flat thing. It's for locating the centers of things. And the idea is you start with true position. True position means the theoretically exact location of a feature of size. So here is a part where there's a position control on these 2 holes. And the true position of those holes is located with basic dimensions. Remember, basic dimensions are theoretically exact. They don't have tolerances, they are exact, and they're theoretical. So they locate the true position of those hole axes. If you could make perfect holes, this is where they would be. Now you cannot make perfect holes, and that's why we need a tolerance, but if a miracle happened and you could make perfect parts, these locate the theoretically exact true position of those hole center lines. Then you apply a geometric control to that feature of size dimensions. So we had, let me back up here. Here are the basic dimensions that locate the true position. And here is the feature control frame that gives the tolerance around which those hole centers can vary. And in the section view at the bottom, I have shown 2 red cylinders that represent the tolerance zone. Position tolerances and basic dimensions always travel in pairs because the basic dimensions are required for showing where the true position would be, and then the feature control frame applies the tolerance, the variation that you can tolerate. This tolerance zone, which is represented here by these red drinking straws, the tolerance zone is the zone within which the actual axis of this hole has to land. It has to be somewhere inside that zone. And that tolerance zone, in this case a cylinder, a drinking straw, that tolerance zone is centered around the theoretical true position. So the center lines of the holes you actually make have to be inside this zone somewhere. The axis of the actual hole can shift around side to side, or it can tilt. It doesn't have to be perfectly straight. As long as it's somewhere inside that tolerance zone, that will be a good part. It will function. And these red things are the tolerance zones. Here's an example from our book with 3 tolerance zones. One of them has a hole that happens to be close to perfect. One of them is off to the side. One of them happens to be tipped. But these are all good holes because their center axis each falls within that tolerance zone. Here's an illustration of a tolerance zone, a kind of an analogy. Parking stalls in a parking lot with cars in them are like tolerance zones for position tolerances. So here, this red car is within its zone, it's between the spaces, and it's centered and it's nice and square. This black car here, it's parallel, it's nice and square, but it's off center. That's okay, it's still within the lines, so that's a good parking. This black car on the left is also within its zone, but it's off to one side and it's kind of at an angle. But all 3 of those cars are within their tolerance zones. I'm going to skip over this. You might remember from a few days ago we mentioned that one of the advantages of geometric tolerancing is that you get cylindrical tolerance zones as opposed to square tolerance zones with plus or minus tolerancing. So here's plus or minus tolerancing that gives you up and down a certain distance, side to side a certain distance, and that gives you a plain old square zone. This is a light red zone within which the actual center of a hole must lie. And we saw a few days ago how that was illogical because you could have a hole that was 5/1000ths away from true position, and if it was off in a 45-degree direction you'd accept the hole, but if it was off in a vertical or up and down direction you'd reject it. So then we looked at how it makes more sense to give them a cylindrical tolerance zone. And with a cylindrical tolerance zone, you have 57% more good parts that you can accept. How do we know it's a cylindrical tolerance zone? We look at this position control here that goes with the hole diameter. There's a symbol for position control. And here's a diameter symbol, and this says the position of this hole center line has to fall within a tolerance zone that has a diameter of 10/1000ths when you make the hole at maximum material condition. And you'll inspect it relative to datums A, B, and C. So the tolerance zone is always the shape of the thing you're locating. If you have a hole, holes are cylinders of course, if you have a hole, then the tolerance zone is a cylinder. I call it a drinking straw. So here is this part with the hole on it. This one happens to be metric. So this says the position of these holes has to, the center axis of these holes has to land within a tolerance zone that has a diameter of 0.2 of a millimeter. And here it is down here. There's that tolerance zone within which the axis must lie. So a cylindrical hole has a cylindrical tolerance zone. If you're controlling the position of a flat thing, then the tolerance zone is 2 parallel planes. Here we are controlling the position of this tab sticking out of this piece. And this feature control frame says the position of the center plane of that flat thing has to land somewhere between 2 parallel planes that are 0.2 apart. And here they are illustrated at the bottom, 0.2 apart. And the center plane of the actual part you make has to land in between there somewhere. Position tolerances always use datums so that we can inspect the position of this part. And you might remember that datums are listed in order: primary, secondary, tertiary. The primary datum, in this case datum A, makes 3 points of contact. The secondary datum makes 2 points of contact, and the tertiary datum makes 1 point of contact. And here is our datum reference frame illustrated at the bottom. We always apply these to features of size, and so we always apply the feature control frame to a feature of size dimension. And we can do that by sticking it right next to the diameter dimension or the width dimension, or we can do it by placing it opposite a dimension arrow. Here is the feature control frame. I think you've seen these before. So here is the symbol that represents position. Here's the tolerance zone. This must be for a hole because it says the tolerance zone is a diameter. And that's the tolerance zone when the hole is made at its smallest size, at its maximum material condition. That's why there's an M in there. Here is what that feature control frame looks like if you do not put an M in it. So this feature control frame says, control the position of this hole center line. It has to land within a tolerance zone that's 16 thousandths in diameter, regardless what size you make the hole. If you do not say an M, then the default is this is the tolerance zone regardless of feature size. With an M, you get a bonus tolerance. Without an M, that's the tolerance zone. You're stuck with it. Last slide. Here is our assignment for today. This is what we're going to draw. And we have a square block with 4 holes in it. This drawing happens to be metric, you might notice. Oh wait, is it? No, it's not. It's inch. Sorry. This is inch. He just is using 2 decimal places. He should use 3. And we are controlling the position of these 4 holes. So here's the 4 holes. There's the feature control frame. Notice it's got an M in the feature control frame. And notice again that basic dimensions and position controls travel in pairs. So you need to make the hole location dimensions basic dimensions. That means you'll need a separate dimension style for these basic dimensions. Then the overall width and height and thickness are not basic dimensions. Those will just get our title block tolerance, so that will be your standard dimension style. And then you'll want to stick these 3 datum identifier symbols on your drawing. And notice that each of these datum identifiers is talking about a surface. So make sure you do not line your suction cup up with a dimension. Have your suction cup out on an extension line away from dimensions, as these are. And holler if you run into confusion about this. We did talk about how to put these symbols on a drawing in CAD a day or 2 ago, so you might want to go review that video. But holler if you run into questions.